Okay guys, so in this video we're going to talk about 7.4 integration of rational functions by partial fractions. Now the idea here is that when we run into integrals of rational functions, a reminder, a rational function is a function with a polynomial divided by a polynomial. Um, Kind of easiest to recognize where x is on the bottom and it's like a polynomial, so like x squared or x plus 2 or whatever. Essentially the idea here is that we want to simplify it a bit, and that is we want to make our rational function a sum or difference of smaller, simpler fractions called partial fractions. The method for doing this is actually the opposite of adding or subtracting rational expressions. So rather than something like here where we take this subtraction here um, and combine it, so as a reminder, when we do something like this, if we're combining this thing, right, we need to get common denominators. So that would be an x plus 2 on this one, and this one needs an x minus 1. So we multiply 2 times x plus 2 is 2x plus 4 over x plus 2, x minus 1. And then we have minus x. So I'm going to say plus just to and put the negative here. So negative x plus 1 over x plus 2, x minus 1. And then we have common denominators, so we can combine them. So 2x minus x is going to be x. 4 plus 1 is 5 over our x plus 2, x minus 1. Or more specifically, if we, whatever. Let's do that again. X plus 5 over, now we can distribute this just for the sake of it. X squared minus x plus 2x is going to be plus x minus 2. So essentially, this is something we will start with in the future, and we want to get it back to this. Well, actually, back to this, more specifically, what we started with. Because this is easy to integrate. This, in this form, not so much, because we can't use u sub to integrate this thing here. So if we were integrating this, maybe the bottom x squared plus x minus 2 would be our u, and that would mean that our du would need a 2x plus 1, and there's no way to make x plus 5 into a 2x plus 1. It's just not possible. And so u sub is out for this. So what we have to do is expand it down to this, because if we were integrating this thing here, this integral of 2 over x minus 1 minus 1 over x plus 2, well, this would be pretty easy because the 2 could come out and it's just the integral of 1 over x minus 1. Well, that's easy. It's natural log of x minus 1. And same thing here, natural log of x plus 2. So this is very doable, this integral, but in this form, this is not. So that's what the point of this partial fraction expansion is to do, is that if we run into a rational function that we can't solve with like u sub or some other more elementary method, then we have to expand it into its simpler form. Or this is technically simplified, but when I say simpler form, I mean simpler fractions that we can definitely integrate. So here's the method. Basically, first of all, we have to make sure that the degree of the bottom is the highest degree. Okay, so if the degree of the top, our numerator, is greater than or equal to the degree of the bottom, our denominator, then we have to start by dividing them. So what I mean by that is if we had like a 3x squared plus 2x over x squared minus 4x plus 5, something like this, these degrees are the same, so we'd have to start by dividing. If this was a cubed, this degree is bigger, so we'd have to start by dividing. But if this was something like this, where we have just an x on the top, the degree is smaller, so we don't have to start with dividing. Okay, so that's the first step. Once that's done, we factor the denominator if possible. A polynomial, just as a reminder, can be factored into a product of linear and irreducible quadratic factors. So that is to say, we will be able to factor it down to either a linear, that is x's, x plus 1, x minus 1, whatever, or a unfactorable or irreducible quadratic, that is like an x squared. So for example, this thing right here, x squared minus 4x plus 5, this is actually not factorable. So it's what we call irreducible quadratic. So this is something that we might have. In either case, what we do is we kind of split it up and use A's and B's and C's and D's, whatever, capital letters here to kind of split this up. So what I mean by that is if we have something that factors down to, let's say, x minus 1, x plus 2, okay? Doesn't really matter what this is. What we'll do is we'll write this thing as a over x minus 1, and then we'd say plus b over x plus 2, and we will solve for a and b. Okay. If we had something that was, it doesn't matter what's on top, but we have like an x plus 3 and an irreducible. So let's say x squared plus 2. So this is not factorable. Well, what we'd have to do is we'd have a over x plus 3, and then we'd have to have a bx, so that's what this thing is here, a bx plus c. So we'd say a bx plus c over this irreducible, x squared plus 2. So anytime we have like a squared, an x squared, plus something like an irreducible quadratic, we essentially have to have a linear on top. Anytime we have a linear on the bottom, we just have a constant on top. These are constants. A, B's, and C's are constants. If we have something that is duplicates, so that is to say like x plus 3 squared. Okay, what we'll do is we'll write this as a over x plus 3, and then we'd have to say plus b over x plus 3 squared. So even though this thing here is squared, it's not a irreducible quadratic, so we don't do a bx plus c, we just have another b, but we have to have one for each power. So if we had a cubed, we'd have to do another one over the cubed, and so on and so forth. And then beyond that, it's any combination of what I've just shown. So we want to factor it completely, and then we need to split it up using A's and B's, and then solve for A and B. And you'll see that in action in just a second. Okay. So one thing to note is this is a pretty common integral in these situations. It's kind of a more generic tangent inverse. It should be a tangent inverse here. So essentially, we have like a simplified tangent inverse where it's like an x squared plus 1, but more specifically, it's actually x squared plus a squared. So that is to say, if we have a quadratic that's x squared plus any constant, doesn't really have to be a perfect square, as we learned from our previous section, then we use this as a method of integration. And that comes up fairly often in our rational, so it's worth noting this one. In the like textbooks so-called reduced table of integrals, which is 120, I think it's like number 17 or something. Anyway, so let's take a look at this. So if we are going to integrate this thing, first of all, we can't use u sub because this is the most complicated portion, and it would be like an x, so that's not really gonna make our life any better, or at least potentially not. We might be able to play around with it a little bit. Something like, if x squared minus 4 was our u, then that would mean that du is x 2x dx. The problem here is that you could solve for an x squared perhaps, and maybe deal with these things if this was an odd power, but because it's an even power, we need to use one of them for our dx, and so u isn't going to work here. So instead, we recognize that it's a rational, and so we're going to use partial fraction expansion. Okay, so the idea is, first of all, we look at the powers. This is an x to the 6th, this is an x squared. So this is bigger on top. So we have to first start by dividing it. So we're going to use long division for that. As a reminder, division, we can only use synthetic division when it's like x plus 1 or x minus 1, just like x plus or minus some constant. It can't be a 2x, it can't be an x squared, it just has to be an x plus. constant, or x minus a constant. So we're going to use long division. A few things to note about long division. As a reminder, we often need placeholders if we're missing terms. I say often because in general it's good practice to do so. In certain situations, depending on what information is missing, you can kind of survive without it. But it's a good practice to recognize that we're missing terms and account for them. So it's x squared plus 0x minus 4 is divided into x to the 6th. Now, again, as mentioned, we're missing an x to the 5th, 4th, 3rd, etc. But since there's nothing in between them, I can kind of survive it by not really placing it. Same thing applies actually here, since it's just a singular term. I don't actually need this 0, but it's still good practice to recognize that this would be like a 0x to the 5th, a 0x to the 4th, etc. All right, but we'll just deal with it as we get to it. Okay, so the idea of long division is we need to match our x squared to x to the 6th. That means we need to multiply it by an x to the 4th. X to the 4th times x to the 2nd is going to be x to the 6th. X to the 4th times 0x is just going to be another 0. So again, this essentially a 0x times x to the 4th would just ensure that the x to the 5ths would line up. And then this one would make an x to the 4th. So minus 4x to the 4th. So again, the placeholders ensure that our like terms line up. And like I said, it's sometimes important. Most of the time it's important, but sometimes it's not so much. All right, so now we subtract everything, which means flip all the signs. These drop off. That's a 0 as well. We get a 4x to the 4th. Okay, now we bring down the next terms, but again, since there are no terms, it's not that important. So now we're trying to match x squared to 4x to the 4th. So we need a positive 4, and we need an x squared. Now, 4x squared times x squared is going to be 4x to the 4th. 4x squared times 0, that's a 0. Again, I don't really need it. Let's go on to this minus. So minus 16x squared. All right, so draw our line, subtract everything. So we have a 0x squared minus that. That's 0. This is going to be a 16x squared. So now we're trying to match a 16x squared with our x squared. So we need a plus 16. 16 times x squared is 16x squared. 16 times negative 4 is 3264. So minus 64. And again, we have some 0 here. So we draw our line, subtract everything. These cancel. 0 plus 64 is 64. This is what we call our remainder. So we would say plus 64 over x squared minus 4, our bottom here. So we have now divided this thing out, and we've simplified it already, so we can integrate a fair portion of it now. So we, instead of integrating this rational here, we're actually integrating this thing here, which is x to the 4th plus 4x squared plus 16 plus 64 over x squared minus 4 dx. Now, if we look at this, this is factorable or integrable. Same here, same here. It's only this that we're having an issue with. Okay, but if we notice, we actually can survive this one because, well, we have a plus, so never mind. I was going to say we might have a table. We actually do have a table probably on this one as well, but whatever. So at this stage, it might even be something we don't even have to go to partial fraction expansion, but we're still going to. Again, if we run into something like this, we'll use it, but I'm not going to go to the table in general in this case. I just want to show the method. So we need to factor or to do some partial fraction expansion on this thing. These we can integrate. So let's go ahead and do that while we're at it. This would be an x to the 5th over 5 plus 4x cubed over 3 plus 16x plus the integral of 64 over. Now the next step is factoring. So we're going to factor this. X minus 2, x plus 2, dx. Okay, so again, we'll come back to these, but we're now here that this is the only thing we're really trying to integrate at this stage. So the idea here is that we rewrite 64 over x minus 2, x plus 2 in its base components. So we don't know what those tops look like, but we do know what the bottoms would look like, because this thing is the sum of two fractions, the fractions being x minus 2 and b over x plus 2. So now what we need to do is we need to solve this thing. So for a and b. So what we do is we multiply. We first get rid of the bottom. So we're going to multiply everything by x minus 2 and x plus 2. Get that off the bottom. We get 64 is equal to a times the x minus 2's cancel, and we get x plus 2, plus b, the x plus 2's cancel here, and we get x minus 2. All right, so now we're going to distribute this thing, the a's. So we get 64 is equal to ax plus 2a plus bx minus 2b. Okay, now it seems like we have a single equation and two variables, and technically x is also a variable, sort of. So it might seem like, oh no, we can't do this, but let's think about our x terms here. Ax plus bx will add up to be the x term over here. What's the x term over here? Well, it's 0. There is a 0x here and then a constant. And so like the x terms have to add up to be this x term. So if we think about this, ax plus bx must be 0x. That is to say, a plus b is 0, right? Because if we lose the x's, it doesn't change this at all. A plus b equals 0. Now, the same concept is with our constant here. 2a minus 2b is 64. So 2a minus 2b equals 64. And you might notice that I'm writing this in what we call standard form in our systems of linear equations. So this is one of the reasons you learn systems of linear equations, is so that you can deal with stuff like this. Now, we can actually get away with this pretty easily. We don't have to use like reduced row epsilon or something. So if you think about this, we can use substitution elimination or elementary row operations from our matrices, convert it into a matrix and do that. But I see that I can easily multiply this top row by 2 and get 2a plus 2b equals 0. 2a minus 2b equals 64, and I can then add the two together. So the elementary row operations we're allowed to do is multiply by a constant or add and subtract any two rows together. So I multiplied by a constant, now I'm going to add the rows together. 2a plus 2a is going to be a 4a. These b's drop, and we get 64. So that tells me then that a is equal to 64 divided by 4 is 16. All right. So we have a is 16. Now we plug it into our other one. We know that a plus b equals 0. So that means 16 plus b equals 0. So that tells me then that b must be negative 16. All right, so we know these two things, a and b. So at this stage, what we do is we go back to that integral of a over b. So as a reminder, or a plus b. So a over x minus 2. So that is going to be 16 over x minus 2 plus b, which is negative 16 over x plus 2 dx. So now we are integrating this thing here. Again, as a reminder, we still had the beginnings of our polynomial that we've already integrated, but we're just working on this now. Okay, so this is just a one, like the 16 can be pulled out. We have 16 times the integral of 1 over x minus 2 minus 16 times the integral of 1 over x plus 2 and dx for both. And so if we integrate this, this is just natural log. So 16 natural log of x minus 2 minus 16 of natural log x plus 2. I didn't write the natural log though. Oops. Let's go back to that. Minus 16 natural log of x plus 2 plus c. And again, we still had our first aspects here, these things. And I copy this and see what I paste in. Let's move these over. Yeah, that will work. let me erase this. I'm being lazy, and in that regard, I probably just it could have been easier to just write it. But anyway, that is our integral. It's those portions plus then these portions, which we had to use partial fraction expansion for. Okay, so again, the idea here is that we first have to divide if the power is greater than or equal to the bottom power. That then gives us oftentimes easy things to integrate, but then we're always often left with a remainder. That remainder then we apply our partial fraction expansion or maybe some other elementary method to integrate it. As mentioned, there's probably a table for an x squared minus a squared. There is one for an x squared plus a squared, but anyway. All right, let's do another one. So in this case, we have x cubed over x squared plus x minus 2. So same thing, this power here is greater on top, so we have to start by dividing it. So we have our x cubed, and again, we could have placeholders if we want, plus 0x squared plus 0x plus 0. It's important just to note that those things have to line up. So if they don't, then or things need to line up. So when it's just an x cubed and the rest are zeros, it's not really necessary, but it's still something worth noting. Here we're not missing any terms, x squared plus x minus 2. So the idea here is we need to match our x squared to x cubed. That's an x. X times x squared is x cubed. X times x is x squared. X times negative 2 is minus 2x. Now we are going to draw our line, flip our signs here. So these cancel, we're left with negative x squared plus 2x, and I'm going to bring that 0 down. All right, now we're trying to match x squared to negative x squared. That's negative 1. Negative 1 times x squared is negative x squared. Negative 1 times x is negative x. Negative 1 times negative 2 is going to be plus 2. Same thing as before, we now subtract. So these are gone. We're left with 2x plus x is 3x minus 2. Okay, this is our remainder. Okay, so here is our remainder. So our quotient here is x minus 1 plus 3x minus 2 over x squared plus x minus 2. Okay, so notice something. When we have like a quadratic, oftentimes we have a linear below, but we'll never have a quadratic on top after that. If there's a quadratic on bottom, the top needs to be linear or maybe a constant. Anyway, so we are now integrating x minus 1 plus 3x minus 2 over our x squared plus x minus 2. I'm going to go ahead and factor that while I'm at it, while I'm rewriting that. X squared plus x minus 2, that factors as x plus 2, x minus 1. Okay, so these are easy to integrate. That would just be an x squared over 2 minus an x plus the integral of 3x minus 2 over our x plus 2, x minus 1 dx. Okay, so again, we need to keep in mind we have those x squared over 2 minus x while we work on expanding this out. So same thing as before, this is just an x, and then like these are just x to the 1 powers here that have been fully factored. So we have our 3x minus 2 over x plus 2 x minus 1 is equal to a over x plus 2 plus b over x minus 1. And we're going to do the same thing, solve for a and b. So first, multiply it off the bottom, x plus 2 x minus 1. That gives us 3x minus 2 is equal to a times x minus 1 plus b times x plus 2. Notice that it's always just the a is multiplied by all the things that it doesn't have underneath it, and b is multiplied by all the things it doesn't have underneath it, and this will always drop off entirely. But so we can kind of start getting lazy in shorthand, but be careful, just don't be so lazy you make mistakes. That's the big thing. You can be lazy enough that you don't make mistakes. So I skip steps if I can do it 100% of the time without making a mistake on it. So I don't skip a lot of steps then, obviously. All right. So we're going to distribute. We get 3x minus 2 is equal to ax minus a plus bx plus 2b. And we're going to use the same logic as before. Our x terms must all add up to be each other. So essentially that is ax plus bx has to equal 3x. Now, I don't normally write it with the x terms. I usually just write it in the simplified, like if we divide everything by x here, a plus b equals 3. That's really what I would write. And same thing here with my constants. We have negative a plus 2b is equal to negative 2. Okay, so same thing here. We don't have to go to like a matrix calculator and simplify this. This is really easy to simplify. If we just add these two rows together, these a's will drop. We get 3b is equal to 1. So that means b is equal to 1/3. Since b is equal to 1/3, a plus 1/3 equals 3. So I don't have to add any fractions. I'm just going to multiply by 3. We get 3a plus 1 equals 9. Subtract 1. 3a is equal to 8. So that means a is equal to 8/3. Okay, so we have those things. I'm going to split it up and rewrite these just so I don't forget about them. So we have x squared over 2 plus x plus the integral. Let's just, I said plus x. In my brain, I knew it was minus x, and I still said plus x. Anyway, minus x. And so this thing has now become a plus b over their parts. So this is a, that's 8/3 over our x plus 2. Plus b was 1/3 over our other one, that was an x minus 1. Okay, so this is just a constant. It can be pulled out when we're integrating it. Same thing with this 1/3. So we have x squared over 2 minus x. So essentially it's just 1 over x plus 2. That's natural log. So it's plus 8/3 natural log of x plus 2 plus 1/3. We pull the 1/3 out, and again, natural log of x minus 1 plus c. And that is our integral. Okay, so again, the actual steps are not overly challenging. It's just kind of a lengthy process. Partial fraction expansion is definitely one of those things that just takes a little bit of time, but otherwise it's not horrible. All right, let's do another one. Okay, so we have an x squared plus x plus 1 over x cubed plus 4x squared plus 5x plus 2. Now, in this case, the top here is not greater than the bottom, so we don't start with division. We're going to start by factoring. Now, how do we factor a polynomial? Well, we have a couple options available to us. We have the traditional method where, if you remember from pre-algebra or pre-calc, excuse me, factoring polynomials, we look at factors of p over q. P over q is a factor of the polynomial if there is a rational factor. And so we're looking for the rational factor theorem. And so essentially factors of 2 over 1, which is just 2. So factors of 2 are going to be all of our rationals. So if we think about it, it's like plus or minus 1 and 2. So that is to say our rational, if there are rational factors of this polynomial, they're either going to be 1, -1, 2, or -2. And so then we use synthetic division to determine which of those they are. So that is to say, we'll use synthetic division. This is not missing any terms, so it's 1, 4, 5, 2. And we now think, okay, well, let's see, maybe like x plus 1 is a factor. If x plus 1 is a factor, then we use synthetic division. It's -1, it's the 0. Oftentimes just it's the opposite sign. The reason why it's the opposite sign, because long division, as a reminder, when we do long division, we always subtract after we find that. So this negative here just takes care of that subtraction step. So it just does the long division really quickly. So we bring the 1 down. -1 times 1 is -1. 4 minus 1 is 3. -1 times 3 is -3. 5 minus 3 is 2. -1 times 2 is -2. 2 minus 2 is 0. So that is a factor. because it has no remainder. So I'm not dividing this by this, I'm factoring this by dividing out an x plus 1 in the hopes that maybe x plus 1 was a factor. That is, the 0 here is -1. Turns out it is. So that's cool. So essentially on top, I haven't done anything with it. It's still x squared plus x plus 1. On the bottom, we have divided an x plus 1 out. So that is, we factored an x plus 1. What's left behind here is an x squared plus 3x plus 2. Okay, so now we are going to continue factoring the bottom. This is now a quadratic, so we can just go to more trivial methods. That is our simple factoring, x plus 1. So this factors of 2 that add together be 3. They are x plus 1 and x plus 2. So notice we have an x plus 1 squared here. So when we split this, that is to say, when we take our x squared plus x plus 1 over x plus 1 squared times x plus 2, what we need to do is an a over x plus 1 plus b over x plus 1 squared plus c over x plus 2. All right, so again, this is a special case where if we have some power, we need to account for all their powers leading up to it. Okay, so we multiply everything through by the bottom. That will give us x squared plus x plus 1 is equal to a times x plus 1 times x plus 2. Because one of the x plus 1's cancel, we're multiplying everything by this thing. Plus b times x plus 2 plus c times x plus 1 squared. Okay, so now these things can really lead to a lot of mistakes if you are not super careful with your multiplication. So you just have to be super careful. Like, don't skip any steps if you are going to make a mistake on things, and even then, just be careful. So I'm going to FOIL these two out and distribute while I'm at it. So I have x squared plus x plus 1 is equal to a times x squared plus 2x plus 1x is plus 3x plus 2 plus bx plus 2b plus c times x plus 1 squared is x squared plus 2x plus 1. Okay, now if we distribute this further, we have x squared plus x plus 1 is equal to ax squared plus 3ax plus 2a plus bx plus 2b plus cx squared plus 2cx plus c. Okay, now this is a little bit more complicated of a system that we're going to create. We have a's, b's, and c's, so we have 3 variables, and we have 3 equations essentially. So let's take a look at our x squareds first. X squared, x squared. So we have a x squared plus 0b, but plus, I'm going to just leave a little bit of a space for it, plus c x squared is equal to 1x squared. So notice I ignored the x squareds here. This is how I usually just start with writing it. Now let's take a look at our x terms. I'm going to also get rid of these so I don't look at them. So now our x terms. Here's our x, here's an x, here's an x. Okay, so that's 3a plus b plus 2c is equal to 1x. So again, I'm not writing the x's here. All right, now I can get rid of these, and I can now focus on the constants here. All right, so that is 2a plus 2b plus c is equal to 1. All right, now technically speaking, we could like add these two, like add a and 2a together to make a 3a, multiply it by -1 and add it and start canceling, whatever. But essentially, instead, what we want to do is, well, what I'm going to do, because I am not going to bother solving a system of 3 equations by hand, I'm just going to make a matrix of it. So let's create a new matrix. So this is in Desmos matrix. This is a 3x4. And so let's talk about what this is as a matrix, first of all, in case you are unfamiliar. So basically our matrix, we write this with just the coefficients. So A's, B's, C's, and constants in this standard form can then be written as 1, 0, 1, 1, 3, 1, 2, 1, 2, 2, 1, 1. So that's our matrix. So we're going to enter that. So we have 1, 0, 1, 1, 3, 1, 2, 1, 2, 2, 1, 1. And we're going to do what we call reduce row epsilon on it. You can also do this on a TI-84, just as a FYI. So this is just going to save us a lot of hassle. Okay, so we get A is equal to -2, B is equal to 1, C is equal to 3. B is 1, C is 3. Okay, so we can revisit this. I'm going to just copy it down here so I have it. Our reference. Okay, so that means we are going to be integrating A, -2, over x plus 1, plus B, 1, over x plus 1 squared, plus C, which is 3 over x plus 2. All right, so we're going to be integrating this thing here. So if we take a look at this, the integral of this would be, oh, and also we had, as a reminder, we didn't have anything ahead of it, so there's nothing we have to really worry about remembering in that case. So this would be a -2 natural log x plus 1. Here we'll come back to it in just a sec, plus the integral of 1 over x plus 1 squared, just so we can revisit this, plus here this would be 3 natural log of x plus 2. Okay, so these ones are easy. Let's take a look at this one though. So this integral here, if we write x plus 1 as u, right, then this would mean that this is a du is equal to just a dx. So essentially we could replace this as the integral of 1 over u du very easily, and we integrate this thing, which is to say, that's an u squared, sorry. So that is to say integral of u to the -2 du. So the integral of u to the -2 is going to be u to the -1 over -1. So that is to say it is -1 over our x plus 1. So this one required a little bit of thought, but these ones are easy. So we have -2 natural log of x plus 1 minus 1 over x plus 1 plus 3 natural log x plus 2 plus c. Okay. So again, sometimes we have to do some long division to factor, but not to simplify. Okay. So factoring polynomials is pretty important. All right, let's take a look at another one. Now, something like this, again, top is smaller than the bottom, so we don't have to worry about it. So we can do long division here, but let me show you another method we have to factor it in a modern world. Okay, this can make it quite easy, is if we graph it. So usually I actually graph polynomials to factor them. Nowadays it's quite easy with graphing programs like this. So if we have something like this is our polynomial. We can tell that it factors into 3 factors here because of the intersections. Now you might say, well, we only have 2 intersections. Yes, but this one here is a multiplicity. We can clearly see that it comes down and just touches it. That is a multiplicity of 2. So we can tell when we factor this thing, 3x squared plus 12x minus 20 over, this is going to be an x. So if this is a 0, x minus 2, then it factors as an x plus 2. Here, if this is an x, this a positive 2 is a 0, that means it factors as x minus 2, and it does it twice. Okay. So again, I just want to show you that factoring is pretty easy if we use a graph instead. It makes it pretty trivial. So we have that as our factor. And again, we are going to have this same special case where we need to split this up. So that is to say our 3x squared plus 12x minus 20 over x plus 2, x minus 2 squared is equal to our a over x plus 2 plus b over x minus 2 plus c over x minus 2 squared. And we are going to do our expansion. So if we multiply everything by our x plus 2, x minus 2 squared, we get 3x squared plus 12x minus 20 equals a times x minus 2 squared plus b times x plus 2, x minus 2 plus c times x plus 2. Okay, so 3x squared plus 12x minus 20 equals a times x squared minus 4x plus 4 plus b times x squared minus 2x plus 2x is gone, so then it's minus 4, and then plus cx plus 2c. Okay, distributing, we have 3x squared plus 12x minus 20 equals ax squared minus 4ax plus 4a plus bx squared minus 4b plus cx plus 2c. Okay, so taking a look at our x squareds, here, 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 we have a plus b equals 3. Get rid of our x squareds. Okay, now let's take a look at x. X and x, I think that's it here. Okay, so negative 4a plus c equals 12. Take care of our x's, they're gone. All right, now our constants, we have negative 20 plus 4a, so that's going to be equals negative 20. So we have a 4a minus 4b plus 2c equals that. So as a matrix, this is just 1, 1, 0, 3, negative 4, 0, 1, 12, 4, negative 4, 2, negative 20. So this is what we're going to plug in. Realistically speaking, again, we could kind of add these if we wanted, but I'm not going to do reduce row epsilon form by hand, or Gauss-Jordan, or Gaussian elimination is what it's sometimes called. Anyway, so 1, 1, 0, 3. I use Gaussian elimination when I am doing it by hand, but since I have a calculator, I'm going to use reduce row epsilon. So reduce row epsilon of this is going to give us our A is equal to negative 2, 5, 4. Negative 2, 5, 4. Okay, so we can now, I'm going to grab this again, just so I have it. Okay, so we are integrating negative 2 over x plus 2 plus 5 over x minus 2 plus 4 over x minus 2 squared dx. Same thing as before, if we think about this as kind of like u equals x minus 2, then our du would just be dx, so that's nice and simple. So this is like saying a 4u to the negative 2, something like that. So it would be 4u to the negative 1 over negative 1. So it would be a negative 4 over our x minus 2, something like that. That's how that would integrate. So just as an aside, we're going to integrate these. Nice and easy though. Negative 2 natural log of x plus 2 plus 5 natural log of x minus 1, or x minus 2, excuse me, minus 4 over x minus 2 plus c. So that's how that integrates. All right. Now, let's talk about something that isn't reducible. So what we call irreducible quadratic. So if we factored it and we get something like this. So this is a linear, this is a quadratic, but we can't factor it. It's not a difference of squares, it's a sum of squares, which is not factorable. Okay, so what we do is we are going to split this up. So this is 2x plus 5 over x minus 2 times x squared plus 2. And we are going to write this as a over x minus 2 like normal, plus, now because this is irreducible, we need a factor 1 lower than this thing. So this is an x squared, we need an x. This was an x, so we always have constants above just x's, but since we have an x squared, we need a bx plus c. So we need the x term, but we also need a potential for a constant, because that constant might just be 0, but we need to allow for a constant as well, so it's going down by 1 degree each time, much like our long division and stuff. It follows the same logic where we need a placeholder, and that's over our x squared plus 2. Okay, so same steps as before. We're multiplying everything by x minus 2 and x squared plus 2. We get 2x plus 5 is equal to a times x squared plus 2 plus bx plus c times our x minus 2. So we are multiplying that whole thing there. So be careful of that. Common mistake is students will just have c times it. That's not the case. All right. So 2x plus 5 is equal to ax squared plus 2a plus, all right, bx squared minus 2bx plus cx minus 2c. All right, so let's take a look at our squareds. Now, first of all, we have no x squared over here, so our x squareds here, a plus b must be equal to 0. Take care of that. This is gone. Okay, now let's take a look at our x's. Here's our only x, so that is negative 2b is equal to 2. Oh, there's a c. Okay, plus c. All right. That's taken care of there. So that's one of the reasons I also like scratch things out, is so that I can then tell if I miss something a lot easier. Okay, 2a minus 2c equals 5. All right, so this thing here is the matrix 1, 1, 0, 0, 0, negative 2, 1, 2, 2, 0, negative 2, 5. Okay, again, go to matrix and type this thing in. Okay, this is 1, 1, 0, 0, 0, negative 2, 1, 2. This is 2, 0, negative 2, 5. All right. So we have a fraction for our a's and b's, which isn't like, impossible. But it's definitely worth noting. If you get something weird, you should just like, did I do this right? Anyway. So we end up with a is equal to 3/2, b is equal to negative 3/2, and c is equal to negative 1. Okay. So if you're ever not sure, like, oh, I have fractions, and it's like, did I really have a fraction? We can always go back and double check. So ax squared plus 2a, bx squared minus 2bx plus cx minus 2c, that checks out. So our x squareds, a plus b equals 0. Our x terms, we had negative 2b plus c equals 2. And then our 5 was equal to 2a and negative 2c. So yeah, I feel pretty confident about it. So it's not like a fraction is, a deal breaker. It's just something to be aware of, that, if you ever get numbers that maybe you don't trust, just check your math. Okay, but yeah, oftentimes it's hard to catch your mistake if you're just looking at it. So instead, just do it again if you're worried. See if you make the same mistake. All right, so we have 3/2 over x minus 2 plus negative 3 halves x minus 1 over x squared plus 2. Okay, so this is what we are integrating now. So what we have here is, this thing kind of looks bad. We would have like a 2x as our u if we did u sub, so u sub's not going to work here, but we can use some thinking here. I'm going to pull this 3 halves out. It's integral 1 over x minus 2 while we're at it. So essentially, if you remember, whenever we have a fraction where the top is separated by a plus or minus, we can split it at that plus or minus. So I'm going to say plus negative 3 halves x, okay, over x squared plus 2 minus 1 over x squared plus 2. So that's what I'm doing, is splitting it. The bottoms we can't split, but the tops we can, because we can add these back together into this because they have common denominators. We can add them. All right, so I should have this integral here, because technically this 3 halves was just with this one. So to integrate this one, nice and simple, 3 halves natural log x minus 2. Over here, this one is our tangent that we have here. We'll use that. But this one, let's first simplify it a little bit. So I'm going to pull out the negative 3 halves, and we get integral of x over x squared plus 2. Well, this we can use u sub for. So that is x squared plus 2 is u. So that means 2x dx is our du. So we need a 2, so we pull out a 2. And that will then enable us to take this negative 3 over 4 now, integral of 1 over u du. So we can integrate this. This thing here, we'll go ahead and do it. 3 halves natural log x minus 2 minus 3/4 natural log of u, but our u is just x squared plus 2. And then we have this thing here. So again, so this is now minus. So this is an x squared plus 2. So as a reminder, we have this thing. If we have an x squared plus a squared, then it's 1 over a tangent inverse x over a plus c. Now our a here is square root 2. Okay, so going back here, this is not a perfect square, but that's okay. We could write it as 1 over x squared plus the square root of 2 squared. And then it is a square. So it's going to be minus, I'm going to just copy this so that I'm not going back and forth. Again, we're applying this rule here. Okay, so paste this in, shrink it down a lot. Okay, so minus, so this is going to be 1 over, I'm going to do a parentheses just to make sure nothing's weird. A, that's our square root 2, tangent inverse of x over square root 2, and then we have our plus c. So that is our integral. Okay. So now we're going to talk about like rationalizing substitution. So sometimes you have a non-rational function that can be changed into rational functions by choosing some u substitution to be a radical expression and squaring it and solving for x. So we sometimes use that. So the point here is that if we have a square root on the bottom, okay, this isn't a rational anymore, but we can if we have a square root, we may be able to rationalize it by multiplying by some square root. So if we said something like, okay, well, the square root of x is u. Well then, by squaring it, x would be u squared. So we can then write this as dx over our x squared, okay? So x squared would be u to the 4th plus our x is u squared times square root x, which is u. Now we need a du of some sort, so we need to get rid of this dx. So if we derive this thing, we get dx is equal to 2u du. So we can replace this dx here with a 2u du over u to the fourth plus u to the third. And now we have the integral, I'm going to pull the 2 out, of u over u to the fourth plus u third. And we can deal with this thing. So let's take a look du. So in this case, we have a u in everything. We can actually cancel one of those u's out by factoring. Essentially, we can cancel anything we can factor. So if we factor out a u, that would be u cubed plus u squared. And so this can then cancel, still a 2. So 2 times the integral 1 over u cubed plus u squared du. And now we are going to factor this. They both have a u squared in common. So that would be 2 times the integral 1 over u squared times u plus 1 du. Okay, and so what we're going to do here is we're going to write it as this 2 is still out in front of this thing. But let's just worry about splitting this up for the time being. 1 over u squared times u plus 1 is equal to a over u plus b over u squared plus c over u plus 1. So this is not an irreducible quadratic. This is just a duplicate. So that's why we have a duplicate here. So that tells us then that 1 is equal to a times u plus 1 plus b times u plus 1 plus c times u squared. So we have 1 is equal to au times u is au squared. Au times 1 is plus au plus bu plus b plus cu squared. And we are going to go with our u's here. Okay, u squareds. So that is a plus c equals 0. Now we're going to go to our u's. A plus b equals 0. And now we're going to go to our constants. B equals 1. So we have our b equals 1. So then a must be -1 since 1 plus -1 is 0. So a is -1. And if a is -1, then c is 1 to make that 0. So we can rewrite this as the integral of a, -1 over u, plus b, 1 over u squared, plus c, 1 over u plus 1. Okay, du. So this one, well, first of all, this is a u to the -2 when we do our integration. This thing here is -1 natural log of u plus, that's a u to the -1 over -1 plus natural log of u plus 1 plus c. So now we can replace what is our u. Our u was square root x. So we have negative natural log of square root x minus 1 over square root x plus natural log of square root x plus 1 plus c. So we can still use u substitution sometimes to get it into a form that we can deal with, like a partial fraction expansion. Even though it technically wasn't a rational to begin with, we can still treat it as such with some u subs. Okay, so again, with u sub, I mean, there's always a chance we might use u sub in some way. It's just something we might do to rewrite our function into something nicer. All right, let's take a look at one more. So if we have 1 over square root x minus cube root x, okay, now we're trying to rationalize this. Okay, well, let's think about this in terms of the fractional exponents. This is 1 over x to the 1/2 minus x to the 1/3. Okay, so what's the common denominator between these two things? That'd be a 1/6. So let's write them both in that case. So this would be 1 over x to the, if this is a 1, this is a sixth, okay? So it's a half, so it's 3/6 minus this would be x to the 2/6. Okay. So now, if we think about that, if we write u as x to the 1/6, that is the sixth root, oops, the sixth root of x. If we write that, we can use this substitution. So this is a 1/6, right? So there's a cubed of them. So this is like saying 1 over x to the 1/6 cubed minus x to the 1/6 squared. That's what these things are. So that will help us in our u sub here. This is 1 over u cubed minus u squared. And we have a dx here, so let's find what we need to have for that. So first of all, I'm going to take everything to the 6th power, so that's a u to the 6 is equal to x. That way I can du it. So that would be 6u5 du is equal to dx. So I can replace my dx with this thing. So we have times 6u5 du. Okay, so we can now rewrite this. This is the integral of, I'm going to pull that 6 out. Oh, that reminds me. While I'm at it, there was a 2 in front of everything. So at the end of this thing, it was 2 times all of that. So I'm sorry, I forgot that. Easy to forget. All right, let's go back over here. So if we have our 6, we pull the 6 out, which I'll forget about later. Cool. All right, anyway. U cubed minus u squared. I find it easier when I have a piece of paper because I can see and make a note of things. So I like do something like this, that I have a 6 here on my paper so I can look at the full page. Unfortunately on Smart Notebook, I can't like look at the whole thing simultaneously. So that's kind of a problem. It's also a problem if you take more than one page to do the problem, obviously. Okay. So here, if you notice, we have a u squared in everything on the bottom and on top. So this would be like a 6 times the integral u squared times u cubed over u squared times u minus 1. So the u squareds can cancel, and we have 6 times the integral u cubed over u minus 1 du. So in this stage, the power here on top is greater. So we need to divide it first. So we can use synthetic division here. So u minus 1 is just a positive 1. We have a 1 u cubed, 0 u squared, 0 u, and a 0 constant. So again, this would be a u cubed plus 0 u squared plus 0 u plus 0, like that. So we have to have those placeholders in our synthetic division. Bring the 1 down. 1 times 1 is 1, 0 plus 1 is 1. 1 times 1 is 1, 0 plus 1 is 1. 1 times 1 is 1, 0 plus 1 is 1. So that's our remainder. We have 6 times the integral of 1. So this is remainder, constant, u squared. So that would be a u squared plus u plus 1 plus 1 over u minus 1 du. All right, we don't have to do any partial fraction expansion with this thing because this is nice and simple. So we'll just integrate this. This is 6u cubed over 3 plus 6u squared over 2 plus 6u plus 6 natural log of u minus 1 plus c. And now we replace our u. As a reminder, u was the 6th root of x. So this would be 6 and 3 makes 2, the 6th root. So that would be x to the 1/6. x to the 1/6 cubed plus 3 x to the 1/6 squared plus 6 root of x plus 6 natural log of the x to the 1/6 minus 1 plus c. And one last simplification. As a reminder, this would be like 3/6, so that is 1/2. This would be 2/6, so that would be x to the 1/3. Okay, so that is 2 times the square root of x plus 3 times the cubed root of x plus 6 times the 6th root of x plus 6 natural log of the 6th root of x minus 1 plus c. And that is our integral. Anyway, so that is our partial fraction expansion, or partial fraction reduction, sometimes called. I don't know, it's whatever. But the point is that when we're integrating our rational functions or something that we can turn into a rational function, a lot of times we have to expand it into more simple terms to get it essentially into either an x squared or an x. That's kind of the goal. So, thanks for watching.